Talking about the rated load, rated life, rated reliability, and then we'll be, if we have sufficient time, we'll start to look into how to calculate the rated load. Rated load means the loads or the bearing capacity as reported in catalogs. Okay, rated load is the load capacity of the bearings as reported in the catalog. Right. So let's first define a few things. The objective of chapter 11 is to select the bearings, not to design the bearings. So it means the bearings are available. These bearings are classified in version type, application, load capacity. So we need to select the proper bearing. So we select the right size for the shaft, and also we select the bearing with the capacity that can sustain the loads supported by the bearing. So selection criteria usually fall into those 5 points. There are others, but those are the main points. First is the availability of space. So whenever you buy a bearing, this bearing should have the dimension suitable to be fit with the shaft and the housing. Maybe you have small sizes, so the machine should be small, so the bearing must be small. You have large machine, so the bearing can be big, okay, because you have enough space. You know, it's about space limitation. The load and its characteristic, if you remember, we talked about types of bearing. Ball bearing can carry combined load, thrust and radial load. So, but some bearings, they cannot carry combined load, like cylindrical roller bearing. They can only carry radial load. So this is also helps you in selecting the bearing. The desired life, so how long this bearing should live inside the machine. The required speed, so if you remember, some bearings, they can be good for high speed like ball bearings, some others no. And definitely the cost. So the bearings, there are a number of problems that may take place and cause failure in bearings. But if we assume that we are mounting the bearing correctly, so we're not hammering the bearing to get fit inside, we are not overheating the bearing to do shrink fit, okay? All of these things, and we're having sufficient lubrication inside the bearing. If all of these are correct, the bearings would fail under fatigue. So it is simply a fatigue issue. So we know the fatigue is when the material is caused or under cyclic load, right? So when the stresses fluctuate, compression tension, and the load is changing with time, so we have what we call a fatigue phenomenon. And the fatigue, what happens is that the small defects inside the material, there is no material without defects, they form cracks, and these cracks will start to propagate, and eventually we'll have kind of separation. So cracks start to grow, and they connect to each other, and you have a failure. So this image here showing a failed inner race of a double roll ball bearing. So you can see the amount of damage in the inner ring, right? So this is simply caused by fatigue. Now in reality, maybe less than 10% of bearings achieve the desired life. So 10% fail due to fatigue. The remaining fail due to improper mounting, insufficient lubrication, and so on, or inappropriate lubrication, maybe using different oil or different grease than the bearing manufacturer recommendation. But so if we assume that the fatigue is the cause of failure, so bearing manufacturer, they do a number of tests on the bearing, and they set certain criteria. So the failure criteria based on bearing manufacturer is that failure would happen when a bit of a diameter 10 to minus 4 of the ball or the roller. So there are rollers here. Yeah? Okay, when they look at the bit generated, if the radius of the diameter of that bit is around 10 to minus 4 of the roller diameter, if you have a ball bearing, maybe the ball has, let's say, 10 millimeter diameter, into -4 of that. If they find this much of defect, they will consider the bearing failed. Other companies, they have different criteria. They look at the surface of defects. If the surface cover 10 to -2 of inch square, they consider the bearing reached to final life or failed. Okay? Does that mean the bearing cannot run? No, the bearing still run, but it is at stage where we need to replace it. So these are the failing criteria when we consider fatigue phenomena. So if we want to define the fatigue life here for the bearing, it means the useful life. So the life of the bearing before we see or notice the damage that's set by the manufacturer into -4 of the diameter or 10 to -2 inch square of failed area. Now, the bearing manufacturer, they defined some life rating, okay, because when they do the experiment, they run the experiment for a certain period of time. Again, after they run the experiment for that period of time, they inspect the bearing and check the amount of failure happened in these bearings. So there is a terminology, we call it the rating life or rated life. So what is this? It's simply the number of revolution, okay, that 90% of a group of bearings will complete before failure. So if I have 100 bearing, I'm running the test. I run the test to a certain period of time. After I finish the test, I'll find only 10% of my bearing failed, while the remaining, they are still healthy. So this set what we call the minimum life or the rated life. So the reliability here is simply 90%. Tamam? Okay. So there's other life is reported like the median life where we have 50-50. So 50% of bearings failed while the remaining 50% is alive. So what is the rated life or what is the magnitude of rated life? Bearing manufacturer, they set the test duration and we have two manufacturers. Manufacturer number 1 and manufacturer number 2. For ball and cylindrical roller bearings, they consider rated life of 1 million cycles. Okay? So they run the bearings during the test to 1 million cycles, then they inspect the bearings. Manufacturer number 2 for tapered roller bearing, and they run up to 90 million cycles. And they do the same, they inspect the bearing, check the criteria. So whenever we deal with ball bearing or cylindrical roller bearing, the rated life for those in the catalog are based on 1 million cycle, while for tapered roller bearings 90 million cycle. Although the bearings, they live for much, much longer time. Okay, but this is the criteria they set for rated life. Now, when we go and select the bearing from a catalog, we usually have multiple information about the bearings. We have the bore size, which is the inner ring diameter, okay, which should match the shaft. We will have the outer side diameter of the bearing that should match the housing, the width of the bearing, and the most important parameter is the dynamic load rating. What is the dynamic load? Now I said that we run to 1 million cycles, huh? So they will have about 2,500 bearing. They are in run. They run together at the same time, and they are under the same load. So the load applied during the test is the dynamic load. Okay. Why it's called dynamic? Because the bearing is in operation. It's rotating. So what is the basic dynamic load rating? Also, we give it the symbol C10. So dynamic load rating, also known in different names. Basic load rating, specific dynamic capacity, dynamic load capacity, basic dynamic capacity, catalog rating or loads. They are all different names, but for the same parameter. So simply is the load that resulting in a life and the rated life. So we apply this load, the bearing will live up to the rated life, okay, with a reliability of 90%. So again, imagine that you have 100 bearing. We apply the load of 10 kilonewton. We run 1 million cycle, and once we inspect the bearings, 10 of them show failure, while 90, the rest, they show no defects or failure. Clear? Now, when we select, our target is to determine what is the catalog rating for our applications. So the catalog rating is not the load applied on the bearing in your actual design. So today, inshallah, we'll learn how to calculate that. Right. In order to calculate the rated life or estimate the rated life, we need to know the relationship between the load, the life. Okay? So if you remember from material science, this is your life, number of cycle, this is stress, and when you draw on a log scale, it looks a linear relationship. Huh? So if we are here, if I decrease the life, I increase the fatigue strength, right? And if I look for a longer life, what happens to the stress? Fatigue strength decrease, right? Yes. So the relation is like this: N increase, S decrease. Right. So same thing in the bearing. The relationship is governed like this. The load, so this is the load on the bearing. Load on bearing times L, life of bearing. Life is power 1 over A is equal to constant. So the load times the life to power 1 over A is always constant. But manufacturer, they give us data. What these data represent? They represent the rated load and rated life. So when you open the catalog, they'll give you that the bore is this much and C10 is this much. So if I have a bearing for 15 millimeter, for example, and it has a rated load of 10 kilonewton, I know that this was done based on a life equals to 1 million cycle, for example, or 90 million cycle. Depending on the type of bearing, you know? So this is for tapered roller bearing, just to remember. So it means here F is 10 kilonewton and L is 1 million cycle for a ball bearing. So this is constant, right? So I can make a relationship between the rated, the values in the catalog, with the desired values, the one for the design. So I have a shaft, for example, and I need to select 2 bearings for it. And I know the loads on the shaft, for example, I have F1 here, F2 here. Okay, so what I do, get the reactions, RA, RB. And this is the load on each bearing, huh?
Yes.
Okay, so the load on the bearing, I will call it FT, tamam? So it means the load in the bearing times the life of the bearing.
1 million.
This is the desired life. So you need the bearing to live for 20 million cycle, 100 million cycle. How many cycle you want the bearing to live? I set here power 1 over A should equal the rated load and the rated life power 1 over A. Because it's always constant. Huh? Because it's always constant. So desired load is the load applied to the actual system you are designing. Desired life is based on the design requirement for how many cycles you need this machine to run without any failure. Tamam? This is from the catalog.
Constant.
Based on size of the bearing, when you go select, and this is constant. Okay? Which is the rated life, the life based on the test by the manufacturer. Which we have two values for it, either 1 million or 90 million, depending on type of bearing. Type. Now, when we want to select, we open the catalog, we search for something. Huh? What we have to search for is the rated load. So this is what we look for. We look for this. Okay? We look for C10 because I want to select a bearing that can carry the load safely and to reach the desired life. So I can manipulate this equation, okay, and rearrange its parameter to be like this. The dynamic load, which is also equal to rated load, same thing, is equal to desired load times desired life over rated life power 1 over. So again, these are design requirements here. This is design requirements based on the design. Also, this is design requirement. This is based on your selection. So you say I want to go with a ball bearing or with a cylindrical bearing, depending on the selection. And we said that the applications are different. For example, if I have very high radial load, I prefer to go with a cylindrical roller bearing. Why? Why cylindrical roller bearing carry larger radial load? Surface contact, because contact is a line in the cylindrical roller bearing. The roller is cylinder like this, while in the ball it's just simply a sphere. So the contact is a point. Telefonat issue. Okay, so this depends on that. If I have a combined load with a little thrust load, I would go with ball bearing. But if I have thrust load, I cannot use cylindrical roller bearing. We can use, this is derived from here, tapered roller bearing. It's derived from both. Okay, here what do we have? With tapered roller bearing, I can carry combined load, thrust plus radial. So in case of ball bearing, A is equal to 3, and those two, A is equal to 10 over 3. No? So again, this depends on your selection. You decide to go with ball bearing, or you decide to go with cylindrical roller bearing, or tapered roller bearing. And we said it's based on the nature of the load, what type of load you have. Rated load, rated F1 life, again based on the type of bearing. If I go with those two, 1, 2, what is that? It's going to be 1 million cycle. If I select tapered roller bearing, it is 90 million cycle. No? So you plug all the values, you get C10. Now you can search in the catalog for the right. Yes.
You said in the selection of the A, you said what's the difference between cylindrical and ball and the tap?
Is in their application. Ball bearing can carry combined load, but the thrust load is poor. A little thrust load cannot carry high thrust load. For high thrust load, you have to go and you combine large radial load and large thrust load. You have to go with the tapered roller bearing. If you remember, we said that the tapered roller bearing has an inclined surface. Huh? So when you have the radial load and thrust load, their resultant still can form a perpendicular to the surface of contact. But for the cylindrical, the radial load is perpendicular while the thrust load is parallel, horizontal. So the roller will slide or slip. For the ball, it can, because the contact is a point, so I can carry both, but still has a limitation on the thrust load. Tamam? Now, one thing we have to be careful about is the life of bearing. The life of bearings, the customer will not come and say that, okay, I need the bearing to live for 20 million cycle, 30 million cycle. He will not tell you that. But what kind of information he can give is the number of operating hours, and the speed of the machine.
Based on that, we find out.
Exactly. Based on that, you can find the life. And sometimes they can give you the application, but without giving you how many hours it should live. So based on the application, you have a range of working hours. We'll show it soon. Right. So if you have the life in hours, and you have the speed in RPM, you can find the life in cycle simply by multiplying life hours by 60. You convert the hours into minutes times the speed in RPM. This will give you the life in cycle. So a simple example, imagine that you want your machine to live for 25,000 hours. Okay, and your speed is 1,000 RPM. So how many cycles you need to make? Can anybody calculate that? So 25 into power of 3 times 60 times 1,000. So this would be how much? 150. شدة 25 كم يا شباب؟ So 150,000. So 4 and another 3, 7. So this is the number of cycles. This is one way of determining number of cycles. So remember, when we want to calculate the catalog rating or the dynamic load, I substitute the life that I want. The rated life based on the bearing selection: ball bearing, cylindrical roller bearing goes 1 million, tapered roller bearing 90 million, and the desired load, which is simply based on my stress, my force analysis. Right? Now my question: how many of you know how to do free-body diagram? Any difficulty with doing free-body diagram? Raise your hand. You have a problem?
Before that,
Yeah.
the catalog rating is the maximum, right?
The catalog rating, it's the capacity of the bearing. I will not say maximum because it is based on certain tests, but the conditions you have is different.
Under this specified test, if it exceeds that, it would fail.
Yes. Okay. It will indicate a 90% passing bearing. So under the same load, 10% has failed already. Okay. So remember, when we deal with bearings, it's not deterministic problem. Statistical things. So reliability, probability to failure appear in the picture.
What if we decrease the load? Can we get reliability more than 90%? Or
Yeah, we'll come to that. The effect of reliability. Yes, if you for example calculate the catalog rating and you found that to be 30 kilonewton, for example, and you went to the catalog and you picked a bearing with a capacity 35 kilonewton. Okay, in this case you enhance the reliability. The reliability will be more than 90%. Okay, because the way we are calculating now is based on reliability equal to 90%. Just to make use of your phones, make sure you have the software application on it. Yeah, let's download this app.
Everywhere.
If you have it, that would be great. Now you go download, not to WhatsApp. Done? Okay, for those who download the app, they can join by typing the username Fadi Al Badur 742, and this will open to you. This question, you see the questions and the multiple choice. Solve the problem and pick the right answer. Yes, any question? Yes.
You said for ball bearing is good to carry combined load, but poor with thrust.
Yeah.
Tubular is good with both. How about this one?
I said it can carry only pure radial load. Cannot have combined. Pure. Just only radial load.
Radial.
There will be
It cannot
sliding.
have. Yeah, there should be sliding.
Which one is this? The cylindrical.
Cylindrical, yes. Cylindrical can only carry pure radial load. Yalla shabab. You have only one answer? So, you can, yes, you have to solve. It's not by guessing. No answer yet? Yeah, it's a ball bearing, and takes a rated life of 1 million cycles. Okay. How many responded? Raise your hand. 1, 2, 3, 4, 5, 6, 7, 8. We simply need to use this equation. So, I'll give you 30 seconds and we'll stop.
Any information about the life? We don't have any.
You have everything. You need just to leg it in. time is about to finish. Done. How many did not respond? Raise your hand. Did not respond. How many? 1, 2, 3. Unfortunately, your answer is wrong.
It is A.
No. Only 17% answered correctly. The remaining, they did not bother themselves to use the equation and calculate. They tried to, do the balancing. I'm reducing half of the load, so I'm extending the life twice, right? Which is not true in bearing or fatigue at all. So this is the equation, sir.
Yes.
So let's put the numbers. 10 kilonewton is equal to 5 times LD. This is what you are looking for, sir. It's telling us view the life. Divided by the radius, which is
Million.
1 million. And what type of bearing is this? Ball. So it's a 3. Can you solve that? Yes. 10 divided by 5 is equal to 2. 2 to power 3 to get rid of that is equal to what? LD divided by 10 to power 6. So this is what? 8
Million.
Why 1 million? 1 million? It's a lot.
So this is the bearing. The catalog rating, the manufacturer set this value. The manufacturer set the life based. So C10 is based on what? The dynamic load is based on a life of 1 million cycle. Okay, I cannot give you the dynamic load without giving you the rated life. So it is the rated load, so it must be with the rated life. And based on what you are reporting this value, for example, of 10 kilonewton, based on the test that was extended to 1 million cycle. Tamam?
One question here. If the rated life or if the rated force is the same as the desired, would we have like the same
The same time.
life?
With a 10% probability to failure. And your question is as follows. If I apply 10 kilonewton here, so if the load is 10 kilonewton, what is going to be the life? It's going to be 1 million.
If the desired as well is 10.
No, if the desired is 8 million, definitely you cannot apply 10 kilonewton. Because if I apply the 10 kilonewton, it means the capacity of the bearing, it will live for 1 million cycle. You get my point? So that was the first part. Let's go to the second part. We start with it and then we. Now, the rating we are talking about, the catalog rating, is based on certain reliability. So, for example, we calculated the life here, right? It was 8 million cycle. But there's a chance of 10% that the bearing not reaching the 8 million cycle. Okay? So there's a 10% probability to failure. So how the number is reliable, the 8 million cycle, is 90% reliable. Okay? So there's a 10% chance that you don't reach the 8 million cycle. Right. Now, is 90% is a sufficient reliability for a design machine?
Yes.
Yes? Let's say, I will not say super critical machine, but a commercial machine.
You have to be conservative, even though.
Well, to be conservative, it's the same. If you select a reliability 90%, are you conservative or non-conservative?
Over conservative. That's what I mean. Actually.
If you go with 90%,
Less than.
less than. Aja, let's understand what do we mean by reliability. Now, reliability, it means how far you are sure, okay, that the machine will do the intended job for the intended life. For example, you design a machine to live for 5 years, okay, and this machine will be under certain amount of load. How sure you are that this machine will reach these 5 years? That's what we mean by reliability. So you say you design it for 5 years, but it may fail before that. Okay, so now if we consider 90% as a reliability, for example, for cars,
Not reliable. Not considered.
it means that the car is not reliable. It means from every 100 car, there's 10 car would fail. So, same thing if you look at pump. If I'm a producer of a pump assembled with motor, there's packages now we have, a small one that you use at home.
Yes.
Okay, so it consists of a motor and coupled directly to the pump. Imagine that from 100 pieces you produce, 10 return to the factory because they failed before reaching the target life. As a manufacturer, what would happen to your your business? Definitely it will fail because it's a lot. A lot of returns would come. So 90% actually is not, let me say, a good value for reliability. Usually engineers, if it's a commercial, they look from 95 and above. And for some critical application, your reliability must be 1. What does it mean? That you are 100% sure that it is running. But now, for machine, it is impossible to have a reliability of 1. So manufacturers do what? They run parallel systems. So you've been into a co-op, I think, some of you. Anybody went to in the plants where they have multiple pumps running in parallel? So they have multiple pumps running in parallel. They operate one during month 1, 2, 3. Then they switch.
Or in case the first one.
Or the case one failed, the second quickly will turn on. صح?
There is some pump for operating. No.
So these are like a standbys, huh? Why?
They cannot stop the production.
Exactly. You cannot afford to stop the production. Imagine if we have a pipeline and a pumping for the oil from one of the fields, and this pump failed. Can Saudi Arabia sell the oil from that field? That's it. Alas, all the production from that field stopped. They cannot sell it. They're not able to pump it to the store farms. Huh? So, what will happen? The country will lose money. Same thing if you apply it to a smaller and smaller manufacturer. Some of the machines must be running continuously. So you cannot afford to stop them. Right. So it means you have to increase the reliability of the selection. Right. So in order to increase the reliability, we will introduce a factor called a reliability correction factor. Do you remember a marine factor? So in marine factor, we used to say that fatigue strength, laboratory fatigue strength is equal to this much, and then we add a correction factor for surface finish, for the type of load, if it's bending axial or torsional, and reliability, temperature, etc. Now the same thing here in the bearing. So remember we had this equation, C10 is equal to, I'll put some bracket here, desired load, desired life, rated life to power 1 over A, and I will put something like that. Those two divided by another factor. So,
This is the reliability factor.
yes, this is the reliability factor. So, let's think about this. If I said that a bearing with a capacity 10 kilonewton can carry a load of 5 kilonewton easily for 8 million cycles, but with a reliability of 90%. If I want to increase the reliability, and I'm still looking for the same life, the capacity of the bearing should be greater or less than 10 kilonewton?
Greater.
Greater. So that's why you see that the correction factor is here. And correction factor is always less than 1. So, now because bearings is all based on statistical analysis, they found that the most suitable distribution for bearings is called Weibull distribution. A Weibull distribution has some parameters, D, X naught, and theta, and those are based on the type of bearing. And you will be using those parameters to calculate the correction factor. Correction factor is calculated as follows. X naught plus theta minus X naught times length 1 over RB to power 1 over B. Okay? So this is now your desired reliability. You want to pick the bearing with a reliability 98%. You substitute here 0.98. While those X, theta, and B, they are based on the bearing, just like when we talked about A and the rated load, rated life. Okay? So we stop here, Shabab. Next class, we will learn how to implement the reliability factor in the equation.